In this video, we want to continue implementing our buffer implementation that uses a singly linked list. So we had gotten through the general setup and the first 4 abstract methods. Because we are implementing buffer, there were 9 methods that we had to include. We've done apply, clear, length, and update because those were the easiest ones and they kind of gave us a feel for what's going on here. Now we need to pick one of the others. Well, the next easiest is probably actually prepinned and then followed by append. So I'm going to go ahead and work on writing prepin. Now I can actually write the last line of this. The last line of the method gives back this, the current object. The reason for doing this is it allows you to string together. So I can take, like in the case of a plus equals, I could say lst plus equals 3 plus equals 7 plus equals 9 to add 379 to the end of the list. And if I use the plus equals colon, then I would put them in front. 3 plus equals colon 7 plus equals colon 9 plus equals colon list. Because it ends in a colon, it is right associative instead of left associative. So, how do we prepend? Well, in many ways, this is very much like the code that we had previously for our special case of adding to the beginning of the list. The head needs to be set to a new node that holds our new data and points to the previous head. We also need to remember, so in our other code, that would have been it. Now in this code, we have 2 other things in here. So in addition to modifying the head, well, I've just added an element. So I need to increase the number of elements. I also need to do something dealing with tail. Even though this is prepending, this is adding before the head, there is a special case now. If the tail is still null, that means that the list was completely empty. It didn't have anything inside of it. Well, in that situation, adding something is both the head and the tail. So if the tail was null, then I have to set the tail to point to the head. Okay, what about appending? Well, maybe we should refer to our picture here. Appending to the list is adding a new element here at the end. Okay, that would be a new element that goes after tail. So I would update tails next when I do this. So the default code to write would be to say tl.next equals a new node of the data that we're adding pointing to null, because it's the last element of the list. It doesn't point anywhere, and as we saw before, we have to give back this. We just added something, so num_elms plus equals 1. I have to say, I often forget to add those in there. I'll have to remember that for both insert all and remove. Well, this line has a problem. Okay, it's actually a very happy line, works very nicely for us under the assumption that there's actually a tail. Okay, if there isn't a tail, if tail was null, which it starts off as, so we know that's a possibility, this line will cause a null pointer exception. Okay, we really don't want to have a null pointer exception, especially since it would happen the first time you tried to add something. That would be bad. So having an empty list is a special case. So we have to check if TL is equal to null. Well, in that situation, we're going to set both the head and the tail to a new node. And so I could set head equals new node of elem and null, and TL equals HD. Else, what if the list isn't empty? What if we have at least one element there? Well, this line right here gives the tails next a new node. So let's go back to our picture. That creates a new node and links this to it. But there's still one step that has to happen. We have to adjust the tail and make it point to the new node. Okay, that's not hard to do. We can set TL equal TL dot next. Okay, we just set the tail's next to be a new node. Then we need to move the tail forward to point to that new node that we just created. That's an append. So we have an append, we have a prepend. We have an apply, we have a clear, remove, insert all, and iterator. I'm going to go with remove next. Once again, I'm increasing in complexity. Insert all just has a certain inherent complexity to it, and iterator is a completely separate kind of concept that we need to talk about. So what happens with remove? Well, with remove, we're going to walk through the list and find the thing that we want to take out. And that part, at least, is very much like what we had done before. We can require that our index is in the right range. We are removing something. So that I don't forget it, I'm going to go ahead and subtract 1 from my number of elements. After doing that, though, just as with all of our other things that we're adding and removing, it turns out there's a special case here. Okay? This singly linked list has special cases anytime head is modified or tail is modified. And in the case of remove, it turns out that either one could be modified or they both could be modified. What if, at this point, num elements was 0? I only had one element, I've pulled it out. Well, in that case, I now have an empty list, and I probably have to do something special for that. Turns out that if you try to handle that in the normal way, things are going to get challenging. So to do that, I will just set the head to null. Actually, no, that's not the right special case. And that is a special case, but I want to write others that will wind up handling it. What if I instead check for I'm removing at the head? And we had that previously. That was a special case for our remove here. If you're removing at index equals 0. So if my index is 0, what do I have to do? Well, I have to give back the value here. So I'm going to remember it, and then I'm going to give it back at the end. Now I need to take out that node. Well, we've seen what this does, how to do this before. I just need to make the head be the head's next. Okay? That's a simple remove. And for our previous code, that could have been sufficient. But going back to the what if there was only one element and we just got rid of it? Well, now head will actually point to null because there was only one element, its next pointer was null, and so we just set head to be null. But at this point, tail wouldn't be null. And having head be null and tail not be null would leave our list in an inconsistent state, which we don't want to do. So we're going to do a check. If the head is equal to null, then we're also going to set the tail to be null before we give back the value that was removed. If it's not the first element, then I need to walk through and find the element before it, okay? In very much the way that we have done these things before. So I'm going to start off the rover at head. I am going to have some variable go from 1 until n, because remember we have to stop 1 shy. Rover equals rover's next. And once we have found the right thing, rover's next data, and then we can give it back. So, oh, I'm missing a minus sign. I was wondering why is this still unhappy? There we go. Okay. So I remember the value that I need to return, and I give it back, and in between those two, I need to link around this. So, as we did before, rover's next equals rover's next next. So that links around the following node. The node after rover gets taken out because basically rover forgets about what has been there and remembers the one after it. But there is, again, a a special case here, because what if the thing we just removed happened to be the tail? Well, if it was the tail, then now this rover is our new tail. If it wasn't, then we don't need to do anything. So we can check. If rover's next is null, that means that rover is now the tail. So we're going to set TL equal to rover. And then we can give back the value, and we'd be done with our remove. So this just leaves two more methods that we need to implement here. An insert all to insert a whole bunch of elements, which of course can be used to insert one element, and an iterator. And we'll have to talk about exactly what that means when we come back and implement these in the next video.